Today you will be learning lesson 4.2 on patterns and linear functions. A function is a relationship that pairs each input with exactly one output. And that's key important. Each input can have exactly one output. Okay? So whatever I plug into that equation, no matter when I do it, okay, I'm always going to get the same answer. Okay? And a function can be represented with words, tables, graphs, or equations. Okay? There's two parts to a function: your input, which is our x values, and your output, which is your y values. That input is also called your independent variable. Okay, so that's something else you need to remember about your input. And those are the values whose value determines the output of a function. Okay, so your input is what we plug into the equation. Okay, or we plug into the function, depending on how it's represented. Okay, it's what we substitute into an equation if it's an equation-based problem. Okay. The output then is what we get out of that. Okay, it's also called your dependent variable. Okay, so it's the variable whose value is determined by the input. So depending what I plug in, okay, determines what I get out. So here I have some examples of functions tables, and we're going to determine if the following relationship represents a function and be able to explain why or why not. The first thing you should check is your input. Okay? Our input on this first one, we have a 1, a 3, a -2, and a -5. They're all different. Okay? That right there should automatically give us a hint that this will be a function. Okay? And if I look at that, a 1 is only paired with a 2. The 3 is only paired with a 4. The -2 is only paired with -1. And the -5 is only paired with 4. So this is a function because each input has exactly one output. Okay, that's right from that definition. Each input has exactly one output. Okay. When I look at this next one, the input, we look at 1 and 4, they're both different, okay? But when I look at this 1, it is paired with both a 1 and a -1. So, and the 4 is paired with a 2 and a -2. That right there tells us it's not a function. Okay, and if we think about the reason why not, okay, each input has more than one output. And that's not allowed for it to be a function. Okay. So last one, when I look at the input, we have -1, -2, 1, and 2. They're all different again, so when we look at those outputs, -1 is only paired with 1. -2 is only paired with 2. 1 is only paired with 1. And 2 is only paired with 2. So even though there's only 2 outputs, and these outputs have multiple inputs, okay, it is a function, okay, because each input only has one output. Each input has exactly one output. It doesn't matter how many numbers the output is paired with, as long as each input is only paired with one number. So let's look at some word forms. Determine if the following represents a function. If so, identify the independent variable and the dependent variable. Remember that independent is our input, Okay, it's the one that we could plug into something to determine something else, so that dependent is our output. Okay. So the speed of a swimmer and the depth of a pool, is there a relationship there? Okay, the speed of a swimmer and the depth of a pool. Okay, so does the depth of a pool determine how fast anybody swimming in that pool can swim? No. Okay, if I were to jump into a 6-foot deep pool, there's no way I would keep up with somebody on the swim team, because I am not a very good swimmer. So this is not a function, because at a depth of 6 feet, we could have multiple speeds. Or we could have the speed of a swimmer at somebody swimming 10 miles per hour. Somebody might swim 10 miles per hour in 6 feet. Somebody can swim 10 miles per hour in 20 feet. Okay, so it's not a function. The growth of a plant and the amount of light the plant receives. Okay? From science class, you should know that the growth of a plant, plants require light to grow. Okay, so this one is a function. Okay, the more light a plant gets, the better it grows. So that makes the amount of light our independent variable. And I'm going to abbreviate independent with an I. And I'm going to abbreviate dependent with a D. So our independent variable is the amount of light. Okay. So a plant receives 2 hours of light, 3 hours of light, 4 hours of light, okay? Versus our dependent variable, that amount of light determines the growth of the plant. The number of books on a shelf and the length of a shelf. Okay. Now we should think the number of books and the length, okay, depending on how you interpret this problem. Okay. But in general, the longer the shelf, the more books it can hold. Okay. So this could also be a function. And you could argue that it could be a function depending on the size of the books. And yes, that's true, but we're going to think about as a function if all our books are the same size for this problem. Okay, so if we're talking about independent versus dependent, the number of books the shelf can hold is determined by the length of the shelf. So the length of the shelf is our independent variable. Okay, whereas our dependent variable then, the number of books depends on how many or how long that shelf is. Okay, so independent versus dependent is what our focus is for these problems. So what we use functions for is to represent different types of relationships. Okay, so in this problem, okay, it says in the diagram below, what is the relationship between the number of triangles and the perimeter of the figure they form? Represent this relationship using a table, words, an equation, and a graph. So they want us to represent this relationship in all the different ways to represent a function. Okay, so I gave you a hint right there, and the first hint is going to be to explain what your variables represent. Remember, when you have a function, you have an input and an output. We have an x and a y. Okay, so for my x, we need to decide, is that input the number of triangles or the perimeter? Which one determines the other? Okay, your number of triangles is your input. Okay, how many triangles there are determines what your perimeter is going to be. Okay, so right there I'm defining my variable for my table headings. Okay, so we're going to have a number of triangles and we're going to have a perimeter. So I'm going to make a table. Okay, And if I look at this one triangle, okay, my perimeter, and perimeter we get by adding it all together, so 3 plus 3 is 6, plus 4 is 10. Okay, there's the first set of data from my problem. Okay, if I have two triangles, okay, if I add up the perimeter, we have 3, and 3 is 6, plus 4 is 10, plus another 4 is 14. Okay, so our perimeter got quite a bit bigger. I don't know what I was writing over here. So 14 there, but over here I should have had a 10. So sorry about that, fix that in your notes. Okay, when I move on to 3 triangles, okay, I have 3 plus 3, again 6, plus 4 is 10, another 4 is 14, and another 4 is 18. Okay, in my last set of triangles, we have 4 triangles in this problem. Again, my perimeter, 3 plus 3 is 6, plus 4 is 10, another 4 is 18, another 4 is 14, another 4 is 18, and the last 4 gives us a perimeter of 22. Okay, so what I did right here was I just made a table. Okay, there's an example of my table. So let's write an equation. And we're going to do the equation next to help us with the words. Okay, so our equation. Now the equation is going to be something you need to actually do some work to find, because you have to figure out the relationship between your x and your y, your input and your output. Okay, so when I look here, if I'm looking at my output, if I notice, I'm going to look for something that's changing. Okay, if it's linear, which we're going to write an equation, they're always going to give you a linear function. Okay, there should be a common difference. And what that is a difference that remains the same between your outputs. So from 10 to 14 is a difference of a positive 4. We're adding 4 every time. From 14 to 18, we're adding 4. And from 18 to 22, we're adding 4. Okay, so there's this common change between all of those outputs. Okay, then there's a common change between all of these inputs. It's going up by 1 every single time. Okay, so for my equation, we need to figure out what I do to my input to get my output. Okay, I know it goes up by 4 every single time. Okay, and if that's the constant that's happening every time, that number becomes a coefficient to your input. Okay, so our output y, okay, is equal to the coefficient, which in our case is 4, because that's our change, okay, of our input. Okay, but when I plug that in, if I plug in 1, 4 times 1 does not give me 10. Okay, so I need to figure out what I do to 4 times 1 to get my actual output. And if I have 4 times 1, I only have 4, which means I would need to add 6 to get that output of 10. Okay, so if I try that with my next number, if I plug in 2, 4 times 2 is 8. 8 plus 6 gives me 14. Okay, if I plug in 3, 4 times 3 is 12, plus 6 is 18. If I plug in 4, 4 times 4 is 16, plus 6 is 22. Okay, so I just found my equation to represent my problem. Okay, so there's my equation. Okay, so let's move on to the graph. Okay. And this will be easier for you guys because you guys have your graph or your table right in front of you, okay? Because what you're going to need is your inputs and your outputs, okay? Now if you notice in yellow up there, I said always label your graphs. So if you notice my graph, my labels, my variables are labeled for that x-axis and that y-axis like we talked about yesterday. Okay, so the number of triangles is independent, so it goes on the x, Your perimeter is dependent, so it goes on the y, okay? And so for my table, the first set of triangles, if I only had one triangle, we found out it has a perimeter of 10. Okay, so that's going to be right here above the 9. So in between 9, we have 10 and 11 before we get to 12. Okay? The next set, when I had two triangles, I had 14 for a perimeter. So that's right here. Here's 12, 13, there's 14. When I have three triangles, I'm up at 18. Okay? When I had four triangles, I was up at 22. So there's 21, there's 22. Okay? And the one thing yet missing on this graph, okay, is our title. Okay? And what this was about was the number of triangles and perimeter, and we were talking about a geometric relationship. So that's what I title my graph. Okay? So what we have left now is to define it in words. Okay? And the words is definitely easiest to figure out after you found your equation. So I'm going to rewrite our equation on this page so we can see it. Y equals 4x plus 6. Okay? So what we do for our words, okay, is we think about what our equation says. And what it says is we take the number of triangles times 4 plus 6 will give you the perimeter of your figure. Okay? Or we could say is equal to, would be a better way to phrase it. So working on with from an equation. So the number of triangles, that's our x, times 4 plus 6 is equal to the perimeter of the shape. Okay? So that's easiest to figure out that word form after you have your equation. Okay, so I just represented that same function as a table, okay, labeling that input, that output, my numbers that they gave us from our picture, in the equation that I found by finding our amount of change, okay, and what I do to that change to get my output, okay, in words that I related to that equation, okay, and then in a graph by plotting the order pairs I got from my table. Okay. So what we just made was a linear function, and that's a function whose graph is a non-vertical straight line. Okay? If a function is linear, it's going to have that constant rate of change that I talked about. Okay? When we looked at that table, I just said every time that y is changing by the same amount, right, that's where that comes from. And that's true for every single linear equation. Okay? And the way we find that coefficient, okay, is through this formula. You find your change in y, and you take it over your change in x. Now for me, for that last problem, luckily, if I look at this, okay, that change in y was 4, that change in x was 1, okay, which simplified to 4. So I knew that was that coefficient, okay, which now you know is called a rate of change, okay. So these next ones should make more sense to you because you'll know where that coefficient in that equation comes from. And if it's linear, okay, you should always be able to write an equation that looks like this, okay? Your output is equal to a number times x plus or minus a number. And this number, this plus or minus here, could be 0, okay? But you figure it out, remember, by looking at what we did, that rate of change. So I knew 4 times 1 was only 4, okay, but I have to get to 10, so I had to take 4 plus 10, or 4 plus 6, sorry, to get to 10. Okay, so it's kind of, right now, trial and error, and you'll learn them tricks with the more practice you do for these. Okay, so this is definitely a formula you're going to want to remember. And this number right here, okay, that coefficient of x is always your rate of change, which is this formula, change in y over change of x. Okay. So let's look at another one. Okay. He wants to decide, is this relationship at the table, okay, and it says at the right, but it's below on my picture, okay, a linear function. So what they're asking me to find out is, does it have a constant rate of change? Okay, if they're asking if it's linear, it has to have that constant rate of change. So I'm going to look at my inputs and my outputs. And I always check the output first. From 8 to 10 is 2. From 10 to 12 is 2. From 12 to 14 is 2. So that output is constant. When I look at my inputs, from 0 to 1 is 1. From 1 to 2 is 1. From 2 to 3 is 1. Okay, so there is a constant rate of change. And we can find it by taking that output, that change in y, which was 2, over that change in x, which is 1. And 2 divided by 1 is 2. Sometimes this isn't going to give you a whole number. It might give you a fraction, and that's okay. Right? So describe it using words, an equation, and a graph. So before I do those words again, I'm going to come up with my equation. I just figured out my rate of change is 2. So when I start my equation, our output is equal to, rate of change goes with x, so 2x. Right? It has to be paired with that. So if I take my input times 2, what do I do to get to my output? Okay, well if I plug in 0, 2 times 0 is 0, I have to get to 8, so 0 plus 8 will give me that output of 8. And it's always good to check it with a couple other ones. So if I were to sub in a 1, 2 times 1 is 2, 2 plus 8 is 10. Perfect. If I plug in the 2, 2 times 2 is 4, 4 plus 8 is 12, so it's checks. If I plug in 3, 2 times 3 is 6, 6 plus 8 is 14, so my equation is correct. Okay, again, that rate of change goes with your x value, that input variable, okay? And you have to figure out that plus or minus based on your outputs from that rate of change. Okay, so now let's use words. Okay, so what's happening in this problem is that our input times 2 plus 8 equals our output. And we don't know what those values are representing right now, so we just need to use our input and our output. So since it had this constant rate of change, I forgot to finish answering this question. Since it had this constant rate of change, this tells me it is linear. So make sure on those problems you answer that. Yes, it is linear. Okay, here's my equation, here's my words, and all I have left now is to do is my graph. Okay, remember your graph you need to label. Okay, so my x, the only thing we know about x is it's our input. The only thing we know about y is it's our output. Okay, so a title, the only thing we know about this relationship is it's a linear function. That's what I'm title my graph. Okay, and then I just need to plot my ordered pairs. At 0, I'm up at 8, so I'm going to put a dot there. At 1, I'm up at 10. At 2, I'm up at 12. And at 3, I'm at 14. Okay? So there's a graph of my function. Okay? So let's look at this one. Okay? Does the set of ordered pairs 0, 2, 1, 4, 3, 5, and 1, 8 represent a linear function? Explain. Okay? So the easiest way to do these ones, if you want to make that table, we can make our x and our y, our input and our output. Okay? The first order pair, remember order pairs are x, comma, y. So my input for the first order pair is 0, the output is 2. Second one is 1, 4. The third one is 3, 5. And the fourth one is 1, 8. Okay? So if I want to decide if this is linear, I can look here. Okay? From 2 to 4, it's going up 2. From 4 to 5, it's only going up 1. From 5 to 8, it's going up 3. Okay? So this isn't constant right here. Okay? And the problem with doing it this way is this doesn't necessarily guarantee me it's not a function, because when I look at the top, this is going up 1, this is going up 2, and this is going down 2. Okay, so since neither one of them is constant, I don't really know for sure right now if it has a constant rate of change. I would have to check all of these change in y's over the change in x's. So an easier way to do it when they're giving you ordered pairs is actually to make a graph. So if I'm at 0 and I put a dot at 2, okay? If I'm at 1 and I put a dot at 4, if I'm at 3, I have a dot at 5, okay? And if I'm at 1, they also have a dot at 8. So the easiest way to think about this is by thinking about the definition of a function, okay? A function says that each input has exactly one output. So these right here, remember, the x's are our input, the y's are our outputs. Okay, and when you think about that, if I look at 0, there is only one answer. But when I look at 1, there is 2 answers. Okay? So right there, I should know that this is not a function, much less a linear function. Okay? And it's not a function because 1 has outputs of 4 and 8. Remember, in order to be a function, each input can have exactly one output. Okay? So there's some rules for linear functions. This lesson is gonna take you some practice. Okay? So maybe watching this a few times and re-looking at that rate of change and how you write those equations might not be a bad idea.